Hello everyone, today we start with 8086 microprocessor. As we know that in 8085 microprocessor there are certain limitations. 8085 is 8-bit microprocessor, that means in that microprocessor we can recognize or we can do the operations only on the 8-bit data, and it has the 16-bit address lines. That means the maximum size of the memory that can be interfaced with 8085 microprocessor is 64 kilobyte. And in 8085 microprocessor we do not have the powerful instruction set. In that 8085 microprocessor we cannot do the operations on the characters or the strings. So to remove all these drawbacks, in 1978 Intel launches a new processor, that is 8086 microprocessor. Now this 8086 microprocessor is 16-bit microprocessor. That means in 8086 microprocessor we can do the operations on 16-bit data, and it has the 20-bit address lines. So that means the memory that can be interfaced with the microprocessor can have the maximum size of 1 megabyte. Now again this 8086 microprocessor is 14-pin IC, and this is available in three different variations depending on the clock frequency. 8086 microprocessor 5 megahertz clock frequency, 8086 2 microprocessor 8 megahertz clock frequency, 8086 microprocessor 1 10 megahertz clock frequency. All the microprocessor work at plus 5 volt power supply. Now in 8086 microprocessor we have the powerful instructions. In this we can do the operations on the characters or the string. Now first of all we do the architecture diagram of 8086 microprocessor. So first we consider the general purpose register. Now in 8086 microprocessor we have the total 4 general purpose register, that is AX, BX, CX and DX. All the registers which are in 8086 microprocessor are 16-bit registers. All the registers which are used in 8086 microprocessor are of 16-bit. So here we have the 4 general purpose register, that is AX, BX, CX and DX. Now these registers are of 16-bit each. AX can be used as an accumulator, as in 8085 microprocessor we have the A. Then BX, CX, DX are the general purpose register that can be used to hold the 16-bit data during the instructions or during the execution of the instructions. Now this 16-bit addresses can be divided into two registers that hold the higher byte and that hold the lower byte, or they can be considered as the separate 8-bit register. So we have the AH and AL for the accumulator, then we have the BH and BL for the PX, for the CX we have the CH and CL, and for DX we have the DH and DL. Here H represent the higher byte register and L represent the lower byte register. So in 8086 microprocessor we have the 4 general purpose register, that is AX, BX, CX and DX. Now this AX is used as an accumulator in 8086 microprocessor. Then this BX is used to hold the data, or sometimes it is used to hold the offset during certain instructions. Then we have the CX. Generally it is used to hold the data, or it can also be used as the counter. If we use the delay programming, or we have to use the counter in the programming, then this CX is used to hold the count. Then DX is again is used to hold the data. Okay, so this AX, BX, CX, DX are of 16-bit and then can be divided into two, that is the higher register and the lower register, and each can hold the 8-bit data. तो अगर आपको 8-bit data hold करना, then we use individual of this. If you want to hold the 16-bit data, then this AX will be used. Then we have the flag register. In 8086 again we have the 16-bit flag register. In 8086 we have the 16-bit flag register, as in 8085 we have the 8-bit flag register and we have the 5 flags. But in 8086 we have the 16-bit flag register, as we say that all the registers which are used in 8086 are of 16-bit. Then out of this 16-bit, only 9-bit is used to represent the flags. That means in 8086 microprocessor we have the 9 flags. Now in 8086 microprocessor these flags are divided into two categories. That means there are two types of flags. One is the conditional flag and another is the control flags. Now conditional flags are used conditional flags are set or reset by the microprocessor on the basis of the result of the arithmetic and the logical operations. That means when we do the arithmetic and logical operations, then depending on the result, this conditional flag can be set or reset. Then we have the control flags. In conditional flags we have the total 6 flags. Now in the control flags we have the 3 flags and they are used to control the certain operations of the microprocessor. So these control flags are not set or reset by doing the arithmetic and the logical operation. By using instructions we can set or reset the control flags to do the certain operation or to control the certain operations. Now these are the reserve bits for the flags. So in the conditional flags we have the total 6 flags, that is the carry flag, parity flags, auxiliary carry flag, zero flags, sign flags. These flags are same as we have in 8085 microprocessor. Now in this we have one more additional conditional flag, that is the overflow flag. Then we have the 3 control flags, that is the trap flag, interrupt flag, directional flag. So this is ODIT. ODIT. Okay, these are the 4 additional flags which are used in 8086 microprocessor. We have these 5 flags which are used in 8085, that is the carry flag. This is set or reset when a carry is generated in doing the arithmetic operation, or a borrow is generated in doing the subtraction operation. Then we have the parity flag. This flag will be set or reset when a even parity is generated in the result when we do the arithmetic and the logical operations. Parity means if we have the even number of ones, then we have the even parity. If there are odd number of ones, we have the odd parity. Then we have the auxiliary flags. This flag is set or reset when there is a carry generated from D3 and it is transferred to the D4. So if a carry is generated that at D3 and transferred to D4, then this auxiliary carry flag will be set. Then we have the zero flag. This flag will be set or when the result is 0. When we do the arithmetic and logical operation, and if the result is 0, then this 0 flag will be set. If result is non-zero, this 0 flag will be reset. Then this sign flag is used when we do the operations on the signed number. So if the result is negative, then this flag will be set. If the result is positive, then this flag will be reset. So these are the 5 flags which we use in 8085 microprocessor. Now in this we have 4 additional flags here. So we have the overflow flag. This overflow flag is again used when we do the operations on the signed number. So overflow means, suppose we have the 8-bit data and we do the operations on that data, arithmetic operations, addition or subtraction instruction. And if the result is suppose comes if the result is of 9 bit, the original number is of 8 bit, and when it is added to another 8 bit number and the suppose the result is of 9 bit, then we say that overflow will occur. Okay, so this overflow flag is used when the signed number is added or subtracted. The overflow flag is again used for the signed number, and when the signed number are added or subtracted, and if the result is out of range, that is again if 8 bit data है और अगर आपका रिजल्ट 9 bit का आ रहा है, then this flag will be set. If the overflow is not generated, then this flag will be reset. Now in the signed number, we know that the MSB of the number is used to represent the sign of that number, and the remaining bit denote to D14 will be used to represent the magnitude of that number. Clear? So if the result is out of range, then this flag will be set. If it is within the range, then this flag remain reset. Then we have the control flags. They are used to control the operations of the microprocessor. Now this is the trap flag. This is used for the single step control. As we do the programming in C or C++, then there are, when we run the program, then there are two options. One is the directly execute the program, and another is the step-by-step operations. So this trap flag is used to do the step-by-step executions. So in the step-by-step execution, microprocessor will execute the instruction वन बाय वन, है ना. तो जैसे आपका सिंपल, आपका अगर प्रोग्राम आप सिंपल रन करते हो तो क्या होगा, सिंपल आपका कंपाइल होगा और एक साथ जो है वो आपको रिजल्ट को शो कर देगा. बट इन स्टेप बाय स्टेप एग्जीक्यूशन माइक्रोप्रोसेसर क्या करता है कि एक एक इंस्ट्रक्शन को एग्जीक्यूट करता है और उसके क्रॉसपॉडिंग अगर आपका कोई रिजल्ट जनरेट हो रहा है तो वो आपको प्रोवाइड करता है. तो स्टेप बाय स्टेप ऑपरेशन इज यूज्ड फॉर द डिबगिंग, कि अगर हमें फाइंड आउट करना है कि प्रोग्रामिंग जो हमने की है उसमें कोई एरर तो नहीं है, तो उस एरर को फाइंड आउट करने के लिए हम सिंगल स्टेप ऑपरेशंस परफॉर्म करते हैं. ठीक है. सो दिस अलाउ द यूजर टू एग्जीक्यूट वन इंस्ट्रक्शन ऑफ द प्रोग्राम एट ए टाइम. तो होल द प्रोग्राम इज नॉट compiled or run at a time. One by one microprocessor is executing the program, and if there is a result, then it shows the result, and this is again used for the debugging. So when the trap flag is set, so by using the instruction we have to set the flag. So when this flag is set, then the program will run in the single mode operation. That means it will execute the program step by step. Then we have the interrupt flag to enable the interrupt enable flip flop of the microprocessor. We use this flag. So to enable the flag we have to write the one, we have to set the flag, or if we want to disable it we have to reset it. Clear? Then by using the instruction we can use the enable the flag or we can disable the flag. Then we have the directional flag. This directional flag is used in the string operation. So in the string operation we have the characters that are stored in the consecutive memory location. Then if it is 1, if the directional flag is 1, then the string byte will be accessed from higher memory address to the lower memory address. So if the string operation in the string operation, if directional flag is set to 1, then we have to access the string from the higher address to the lower address. That means we move in this direction, because suppose we have this memory, so in the memory we have the lower register here, we have the higher register here. So in the when the directional flag is 1, we move from the higher register to the lower register, and when it is 0 we move from the lower to higher. So these flags are used to control the operation of the microprocessor. ठीक है. So this is the flag register which is used in 8086 microprocessor. Now in 8086 microprocessor we have the 20-bit address bus. Now because of the 20-bit address bus, the memory size which can be interfaced with microprocessor 8086 is maximum 1 megabyte. ठीक है, तो it can address a maximum of 1 megabyte of memory. Now this 1 megabyte of memory is divided into 3 logical segments. So physically we have the 1 megabyte memory, but it is divided into 16 logical segment. Each segment is of 64 kilobyte, as we show in this figure. So this is the total 1 megabyte memory, and this 1 megabyte memory is divided into the 16 logical segment. So these are the 16 logical segment. Each segment is of 64 kilobyte. Now out of these 16 logical segment, only the 4 logical segments are active at a time. जिसका 16 लॉजिकल सेगमेंट्स हैं, उसमें से एट ए टाइम हमारे केवल 4 लॉजिकल सेगमेंट्स ही हमारे एक्टिव होंगे. सो द 4 लॉजिकल सेगमेंट्स विच आर एक्टिव आर नोन एज द कोड सेगमेंट, स्टैक सेगमेंट, डाटा सेगमेंट एंड द एक्स्ट्रा सेगमेंट. तो जो हमारे यहाँ पर 16 सेगमेंट्स हमने यहाँ पर इसे डिवाइड किए हैं, सो दीज 16 सेगमेंट्स आर further divided into 4 different segments. One is the code segment, then another is stack segment, data segment and the extra segment. So we have the 4 code segment here, we have the 4 stack segment, we have the 4 data segment and we have the 4 extra segment. तो total हमारे पास 16 segments हो गए. 4 code segment हो गए, 4 stack segment हो गए, 4 data segment हो गए और 4 extra segment हो गए. Now out of these 4 code segment, only one code segment will be active at a time. Out of these 4 stack segment, only one stack segment will be active at a time. Out of these 4 data segment, one segment will be active at a time. And out of these 4 extra segment, one segment is active at a time. So we have the 4 segment that are active at a time. One for the code segment, one for the stack segment, one for the data segment and one for the extra segment. So suppose we have this one. So suppose this is the code segment, this is the stack segment, this is the data segment and this is the extra segment. So out of these 16 segment, only the 4 segment will be active at a time. One from the code, one from the extra, one from the stack and one from the data. Now how these segments are decided? These code segments are used to store the different type of data. ठीक है, इन segments को हमने 4 different segment में क्यों हमने divide किया? क्योंकि these segments are used to store the different type of data. Now this code segment store the instructions for the microprocessor. Now in 8085 microprocessor, when we write any program, so in the same memory we write the instruction, then we have the data, we have the instruction and we have the data. So that means in 8085 microprocessor, in the same memory or in the same conjugative memory location, we have the instructions and the data. तो वहाँ पर हम ये डिफ्रेंशिएट नहीं कर सकते क्योंकि सारे जो कोड्स हैं वो हमारे हेक्साडेसिमल में ही लिखे होते हैं. सो इन दैट वी कैन नॉट डिफ्रेंशिएट विच इज़ द डाटा एंड विच इज़ द इंस्ट्रक्शन, है ना. तो हम वहाँ पर ये डिफाइन नहीं कर सकते कि कौन सा हमारा इंस्ट्रक्शन है या कौन सा हमारा डाटा है. तो इस प्रॉब्लम को भी रिमूव करने के लिए 8086 में हमने डिफरेंट टाइप ऑफ डाटा को या डिफरेंट टाइप ऑफ इंफॉर्मेशन को हमने डिफरेंट टाइप ऑफ सेगमेंट्स में डिवाइड कर दिया. तो दिस कोड सेगमेंट होल्ड द इंस्ट्रक्शन ऑफ द प्रोग्राम. तो अगर हमने कोई प्रोग्राम सपोज लिखा है तो उस प्रोग्राम में जितने भी हमारी इंस्ट्रक्शंस होंगी, ठीक है, उस प्रोग्राम में जितनी भी हमारी इंस्ट्रक्शंस होंगी दैट आर स्टोर्ड इन द कोड सेगमेंट, ठीक है। सो दिस इज द पार्ट ऑफ द मेमोरी फ्रॉम विच द माइक्रोप्रोसेसर इज फैचिंग द इंस्ट्रक्शन। So that means this segment hold the instructions for the program or for the microprocessor. Clear? Then we have the stack segment. As we know in 8085, when we write any subroutine, then we have to store some data in the stack. So when we use the store the data in stack, we have to define the stack in that by using the stack pointer. So here we divide the memory in stack segment. So this section of memory is used to store the addresses and the data when we execute the any sub program or subroutine. तो इसका जब हम किसी भी सबरूटीन या सब प्रोग्राम को एग्जीक्यूट करेंगे तो वहाँ पर हमें जो एड्रेसेस और डाटा हमें स्टोर करने हैं, तो दैट डाटा और स्टोर विल बी स्टोर्ड इन द stack segment. Then we have the data and the extra segment. These segment is used to store the data. तो जो हमने प्रोग्राम लिखा है तो उस प्रोग्राम में जो भी हमारा डाटा यूज हो रहा है जिसके ऊपर हमें ऑपरेशंस करने हैं, तो that data will be stored in the data segment. If the data is in the large quantity, then we can use the extra segment in combination with the data segment to hold the data values that is used in 8086 microprocessor. So these are the four different segments that are used to store the different type of information. So code segment is used to store the instructions. Stack segment is used when we use the subroutine or subprogram. Then during that subprogram execution, we store the addresses and the data in the stack segment. Then the data which is used in the program is stored in the data in the extra segment. So these are the four different segments which are used in 8086 microprocessor. So we have the four code segment, we have the four stack segment, we have the four data segment, we have the four extra segment. Out of these four code segment, one code segment will be active. Out of these four stack segment, one stack segment will be active. Out of these four data segment, one data segment will be active. Out of these four extra segment, one extra segment will be active. ठीक है, तो जरूरी नहीं है कि वो हमारे पास पासों जैसे भी हमने कहा था कि 3 4 5 6 हमने यूज किए एज अ कोर सेगमेंट, स्टैक सेगमेंट, डाटा सेगमेंट और द एक्स्ट्रा सेगमेंट. They can be at the different location also. So in this, suppose this segment is used for the code segment, this segment is used for the data segment, this code is used for the extra segment, and this code is used for the stack segment. ठीक है, तो यहाँ पर हमारे जो हैं वो जरूरी नहीं है कि वो हमारे कंसेक्यूटिव लोकेशंस पे ही हमारे सेगमेंट्स हों, हमारे सेगमेंट जो हैं वो डिफरेंट लोकेशंस पे भी पॉसिबल है. तो आउट ऑफ दिस 16 segment, 4 segment will be selected at a time. One for the code, one for the data, one for the extra, and one for the stack segment. So how we decide or how we determine which segment is currently active, कि 16 में से कौन सा हमारा कोड सेगमेंट के लिए एक्टिव है, कौन सा डाटा सेगमेंट के लिए एक्टिव है, कौन सा एक्स्ट्रा सेगमेंट के लिए एक्टिव है, या कौन सा हमारा स्टैक सेगमेंट के लिए एक्टिव है. तो हम कैसे डिटरमाइन करेंगे कि कौन सा सेगमेंट हमारा किस पर्टिकुलर सेगमेंट के लिए एक्टिव है. सो फॉर दैट इन 8086 microprocessor we have the segment registers. So these there are 4 different segment registers. They are used to hold the starting address of the active segment. कि जो सा भी सेगमेंट हमारा एक्टिव होगा उस पर्टिकुलर सेगमेंट का जो स्टार्टिंग एड्रेस है, तो दैट एड्रेस विल बी स्टोर्ड इन द सेगमेंट रजिस्टर. So this code segment register is used to store the 16-bit address, 16-bit starting address of the active code segment. This data segment register is used to hold the starting 16-bit address of active data segment. Then stack segment register for the is used to store the 16-bit address starting address of the active stack segment. Similarly for the extra segment, as we say that each registers in 8086 is of 16-bit. So again these segment registers are also of 16-bit. ठीक है, तो कोड सेगमेंट रजिस्टर, डाटा सेगमेंट रजिस्टर, स्टैक सेगमेंट रजिस्टर एंड द extra segment register, they are used to hold the 16-bit starting address of each active segment. तो इन्हीं से हमें पता चल जाएगा कि कौन सा सेगमेंट हमारा किस पर्टिकुलर इंफॉर्मेशन को स्टोर करने के लिए एक्टिव है. ठीक है. नाउ सपोज वन थिंग मोर कि व्हेन वी हैव टू communicate with the memory, then we have to generate the 20-bit address, है ना, क्योंकि हमारी जो मेमोरी है वो हमारी 1 मेगाबाइट की है, फिजिकल मेमोरी 1 मेगाबाइट की है. तो जो हम मेमोरी के साथ कम्युनिकेशन करेंगे then we require the 20-bit address. But here the registers which are used in 8086 microprocessor can only hold the 16-bit information. So the segment registers which we discuss here, they can hold only the 16-bit starting address. But while communicating with the memory location, we require the 20-bit addresses. Then how we generate the starting 20-bit address of this particular segment? So they are suppose this code segment is start from 10000. These are written in the hexadecimal. If you want to convert it into the binary, each hexadecimal digit is represented by 4 bit. So it is 0001, then 0000, 0000, 0000. Then this is a 4 means 0100 and remaining 0. 50101 remaining 0, F1111 remaining 0. So these are the 20-bit address of the active segment. Okay. Out of this 20-bit address, this starting 4-bit, this starting 4-bit is held in the stack segment register. So this 1000 when hexadecimal is stored in the code segment register, 4000 is stored in the data segment register, 5000 is stored in the extra segment register, and F000 is stored in the stack segment register. So this is the starting 16-bit address of the particular segment that is stored in that particular segment register. Then how we generate the 20-bit address? Because as we communicate with the memory, we require the 20-bit address. Now to generate the 20-bit address, the BIU, that is the bus interface unit. In 8086 microprocessor, we divide the whole architecture into two parts, or the two units. One is the bus interface unit and another is the execution unit. In the later on, we discuss both. In bus interface unit, to generate the 20-bit address, starting address of the particular segment, we insert the zeros in the lowest 4-bit. Okay, in the lowest 4-bit, we insert the 4 zeros. Suppose we have the code segment register that holds 348A. So 348A, for the 3 where you have to write 0 0 1 1, then the 4 0 1 0 0, sorry, then for the 8 1 0 0 0, Then for the A we have the 1 0 1 0. So this is the 16-bit address which is held in CS, that is the code segment registers. Then we have to insert the 40 at the lowest 4 bit. So we have to add these 40. Then we have to make the combination of 4. So this is 3 4 8 A 0. So this will be the starting 20-bit address of the code segment. So this is how we generate the starting address of any segment. So कोई भी एड्रेस हमें गिवन है, तो कोई भी एड्रेस अगर हमें गिवन है तो उसके जो लोअर 4 बिट्स हैं उसमें हमने 0 को इंसर्ट करना है. तो दिस गिव द स्टार्टिंग एड्रेस ऑफ द कोड सेगमेंट. So this is how we generate the 20-bit address. So 64 kilobyte segment can be located anywhere in the memory, but will start at the address with 0 in the lowest 4 bit. क्लियर. तो यहाँ पर हमारे पास जो मेमोरी है, so we have the 16 segment. इन 16 segment में से हम कोई सा भी segment यूज कर सकते हैं कोड सेगमेंट के लिए, कोई सा भी सेगमेंट यूज कर सकते हैं डाटा के लिए, कोई सा भी एक्स्ट्रा के लिए, कोई भी स्टैक सेगमेंट के लिए, है ना. बट हमें करना क्या है कि जो भी हमारे पास ये स्टार्टिंग एड्रेस है उसको हमें 16 बिट एड्रेस जो है उसे हमें स्टोर करना है पर्टिकुलर सेगमेंट रजिस्टर में, और लास्ट में हमें 4 जीरोस को इंसर्ट करना है. इन द माइक्रोप्रोसेसर BIU will insert these 0 at the lowest 4 bit to generate the 20-bit address. ठीक है. तो ये तो हो गया हमारी स्टार्टिंग एड्रेसेस की बात. अब अगर हमें किसी पर्टिकुलर इंस्ट्रक्शन को रीड करना है फ्रॉम द मेमोरी, दैट इज वी हैव टू रीड द पर्टिकुलर इंस्ट्रक्शन फ्रॉम द कोड सेगमेंट. To read the particular instruction from the code segment, we have to give the offset of that memory location to the microprocessor. That offset is stored in the instruction pointer of the microprocessor. So again, this is of 16-bit register. It holds the 16-bit offset of the next instruction byte in the code segment. ठीक है. तो इन 8085 microprocessor as the role of the program counter is the register that point to the memory location from which next data byte has to be fetched. So this instruction pointer works as the same. It holds the 16-bit offset and point to the memory location from which next instruction has to be fetched. Now this 16-bit offset is of code segment. As in 8086 microprocessor we have the different information in different segment. So this instruction pointer holds the offset in the code segment. Then we use the bus interface unit use this instruction pointer and the code segment register to generate the 20-bit address of that instruction of that memory location from which next instruction has to be fetched. So this is how we generate the 20-bit address by using the offset. So suppose the starting address of the code segment is 348A0. So 348A is held in the code segment. Then we want to read the instruction from the memory location 38AB4H. So we have to read the instruction from this memory location. Then we have the physical address, this one, the 20-bit address which is used to communicate with the memory location is known as the physical address. So here the physical address is of 20 bit, that is A38AB4, from which we have to read this instruction. Then how we calculate the offset? So we have the starting address and we have to read the instruction from this memory location. So the difference between these two memory location is known as the offset. ठीक है, स्टार्टिंग एड्रेस हमारा ये हो गया और जहाँ से हमें मेमोरी लोकेशन से इंस्ट्रक्शन को रीड करना है तो दोनों के बीच का जो डिफरेंस है, मेमोरी लोकेशन का जो डिफरेंस है, दैट इज नोन एज द ऑफसेट एंड दिस ऑफसेट इज स्टोर्ड इन द इंस्ट्रक्शन पॉइंटर. ठीक है, तो दोनों का हम डिफरेंस निकालेंगे. दिस इज स्टोर्ड इन द इंस्ट्रक्शन पॉइंटर. सो दिस इंस्ट्रक्शन पॉइंटर होल्ड 4214H. Again we say that this is of 16 bit and this is also of 16 bit, but BIU insert the 0 at this place at the lower byte and sorry at the lower 4 bits, and then we add this code segment register with instruction pointer address register. Then we do the simple addition. So we insert BIU, insert the 0 here, then we do the simple operation, addition operation. So this is how we the BIU generate the physical address to read the instruction from any particular memory location. So this 4 bit 348A is held in the code segment register. This 4 bit sorry this 16 bit address is stored in the code segment register 348A. This 16 bit address is held in the instruction pointer. Then BIU first insert the 4 zeros in the lower 4 bits, then add the instruction pointer register with this address to generate the 20 bit physical address. तो यहाँ पर हम 0 insert कर देंगे और इसको हम इस टाइप से लिख के we do the simple addition, binary addition. So this is how we generate the physical address. And then we have the stack segment register. As we know that the stack segment register containing the 16-bit starting address of the stack segment. So the starting 16-bit starting address of the stack segment is stored in the stack segment register. Now it is located in BIU, that is the bus interface unit, and the offset of this stack segment is stored in the stack pointer register. So stack pointer register is the register that holds the 16-bit offset from the start of the stack segment, and this stack pointer is located in EU. Then we have the other pointer and the index register, that is the base pointer register, source index register, destination index register. Base pointer register is the register, again this is of 16 bit and it contains the offset of the data segment or the extra segment. Then source index register and the destination index register are used when we are performing the operation on the strings or the characters. So this is the summary of this. We have the segment register and we have the pointer and the index register that hold the offset of that particular segment. So we have the code segment. The code for the code segment, the starting address of the code segment is stored in the code segment register, and the offset of this code segment is stored in the instruction pointer. Then we have the stack segment. The starting address of the stack segment is stored in the stack segment register, and the offset of this is stored in the either in the stack pointer or in the base pointer. Mainly it is stored in the stack pointer only. Then we have the data segment. Then the starting address of data segment is stored in the data segment register, and the offset of this is stored either in BX, that is the general purpose register. We have the destination and the source index that is store the offset when we are doing the operation on the strings. Then we have the extra segment. The starting address of extra segment is stored in the extra segment register, and the offset of this is stored in the destination index for the string operation. So this is all about the registers which we are using in 8086 microprocessor. Now in the next lecture we start with the pin diagram of 8086. So thank you.